All right, so we're going to continue sections 13.5 and 13.6 by working up some exercises from y'all's textbook. So we're going to start in 13.5. I'm going to bounce back and forth between the two. We're on page 861, and we're going to start with number 6, which says in exercises 1 through 14, find the directional derivative of f at the point P in the direction of A. All right, so they give us for number 6 that f of xy equals sine of xy squared. So f of xy equals sine of xy squared. They tell us that p equals 1 over pi comma pi. P equals 1 over pi comma pi. And they tell us that our vector A is equal to 1, negative 3. All right, so first off, the directional derivative formula, just as a reminder. So d sub u of f at x naught, y naught equals, you can write as the gradient of f dotted with a unit vector, or f sub x at x naught, y naught. And I'm going to switch and use u1 and u2, although I use a1 and a2 before. u1 plus f sub y of x naught, y naught at u2. And I'm not using a because remember, you need to have a unit vector. So I want to make sure that I don't use the components of that specifically. If it's not a unit vector, if it's a unit vector, that's fine. So that is your first order of business, is determine, is this a unit vector? So the length of A equals the square root of 1 plus 9, so the square root of 10, which is not equal to 1, which tells us that that thing is certainly not a unit vector. So we need a unit vector that points in that direction. So that would just be the vector 1 divided by the square root of 10, comma, negative 3 divided by the square root of 10. So now we're pointing in the right direction, but we have a unit vector. So now all we need to find f sub x and f sub y and evaluate those at this point. So f sub x equals, so the partial of this with respect to x, so we're treating y as a constant, so we would get cosine of xy squared times the derivative of the inside with respect to x, and you would just get, that's a constant times x, so you're just going to get the constant. So we'll just have y squared there. And let's go ahead and find f sub y. F sub y, partial of this with respect to y, you're going to get cosine of x y squared. Oops, sorry, I forgot to take a derivative. Oh no, I didn't. I'm fine. I was thinking of that. All right, cosine of xy squared times the derivative of our inside now with respect to y. So this is a constant, so you're just going to get 2xy. This times 2xy. Now we need to take and plug our point in to here and into here, and then we'll put all of this information right there. Excuse me, right there, and we'll have our directional derivative. So f sub x of 1 over pi comma pi equals cosine of 1 over pi times pi squared. So that's just going to give us cosine of pi, and then times our y squared, so then times pi squared. So this equals cosine of pi gives us negative 1, and then times pi squared, so we get negative pi squared. And over here, f sub y evaluated at 1 over pi comma pi. So we still end up with cosine of pi for that part because we're putting in 1 over pi and then times pi squared, which just gives us cosine of pi. And then 2 times 1 over pi times pi, which just gives us 2. So we get 2 times -1 and -2. Now we take all of this and put it in to this formula right here. So d sub u of f at our point, which is 1 over pi comma pi, equals f sub x at our point, which is -pi squared, times u1, which is 1 over the square root of 10, excuse me. So that gives us over square root of 10. And then plus f sub y at our point, which is -2, then times the -3 over 10. So that's going to give us over root 10, excuse me, 6 over the square root of 10. All right, and that will be our directional derivative there. All right, so now let's look at, notice in doing directional derivative problems, you're finding the gradient vector in there anyway. So if you know how to do a directional derivative problem, you certainly know how to do a gradient problem. But now we're going to look at just a gradient problem by itself. Those are all in 13.6. So let's switch gears. And 13.6 exercises are on page 867. So page 867, and we'll look at number 4. Number 4 says, in exercise 1 through 8, find the gradient of the function, and they give us f of xy equals xy minus 1 all over x squared plus y squared. So the gradient of f of xy. So I said that when you do directional derivative, use the gradient. We didn't write it out as a vector in that problem, although we could have, and then just dotted it with the unit vector. So when you're asked for the gradient itself, you certainly need to write it out as a vector. So this equals, I don't think that's going to fit on this line, so I'm going to go down here. So now, first I need to, well, actually I'll do this. Let's write out what it is. So it's going to be f sub x comma f sub y, which is equal to, we take the partial of this with respect to x. So taking the derivative of the numerator, treating y as a constant, the derivative of the numerator is just going to be y, because this derivative is y, that's 0, times the denominator stays the same, x squared plus y squared, minus the derivative of the denominator. Now with respect to, oh sorry, I don't know why I was doing y, I'm supposed to be doing x. I don't know how I got on y. So the derivative of the numerator with respect to x, I said y, but I did x. So the derivative of the numerator with respect to x is y. So that is correct. I just said the wrong thing. Times the denominator stays the same. Then minus the derivative of the numerator with denominator, sorry, with respect to x is 2x. Then times the numerator stays the same. xy minus 1 all over our denominator squared, x squared plus y squared, quantity squared, comma. Now we are looking at doing the partial of this with respect to y. The partial of the numerator with respect to y is just x, times the denominator stays the same, x squared plus y squared, then minus the derivative of the denominator with respect to y, which is going to be 2y, times the numerator stays the same, xy minus 1, all over x squared plus y squared, quantity squared. So again, please keep in mind that the gradient is a vector. So the fact that these have the same denominator doesn't matter. You're not adding these or doing anything like that with them. All right, so that's it for just finding the gradient vector. They didn't ask for directional derivative, so there's not a directional derivative or anything. So there's nothing else to do on that problem. Let's look at another problem in this section. We'll look at number 10. Number 10, which says, in exercises 9 through 14, find the gradient of the function at the given point. So they give us f of xy equals x times cosine of xy, x times cosine of xy, and they give us the point 1 comma negative pi. So the point 1 comma negative pi. So we need to compute the partials of this with respect to x and y, then put in this particular point, but they want the vector. So we need to make sure we keep it in vector form. So you can do it outside of the vector form and then make sure you put your answer in vector form at the end, or you can do it like we did before and put it in vector form immediately. So the partial of f with respect to x, so here we have a function of x times another function of x. So the derivative of this with respect to x is 1 times that stays the same, which just gives us cosine of xy, then plus this part stays the same, and then the derivative of this with respect to x. So we're going to have minus because the derivative of cosine, and then we're going to have our x there, and the derivative of cosine is negative sine of xy, and then times the derivative of the inside with respect to x is just y. We're going to have another y out there. All right, then partial of, let's go ahead and just plug our point in now because I don't have a lot of space. So f sub x of 1 comma negative pi equals cosine of 1 times negative pi, or cosine of negative pi, which is the same as cosine of pi, which is negative 1. And then minus our x, which is 1, then sine of negative pi. Sine of negative pi is 0. So this is just going to be negative 1. So we get negative 1 minus 0. All right, now f sub y equals, so we're taking the partial of this with respect to y. Constant multiple rule says that x is not going anywhere, so we can just put that x there. Then the derivative of cosine is negative sine, so I should put a negative sign out here. Then sine of xy, and the derivative of the inside with respect to y is just x. So we'll get another x out here. I'm going to go ahead and put it up here. And that's what we get there, negative x squared sine of xy. So we need to evaluate this at our point 1 comma negative pi. So the 1, then for our x, we just get negative 1, and then sine of negative pi, that just gives us 0. So we just get 0 here. So now remember, your answer should be in vector form. So the gradient of f at 1 comma negative pi equals the vector negative 1 comma 0. All right. And let's look at another problem from this section. This is more of an applied problem. So let's look at number 18. So number 18 says, in exercises 15 through 20, find the direction in which f increases most rapidly at the given point and find the maximal directional derivative at that point. So here they give us f of x, y, z equals f of x, y, z equals the natural log of x squared plus y squared plus z squared. And they give us the point 2, 0, 1. All right, so they asked for the direction in which f increases most rapidly. And from our notes, we know that f increases, so f increases most rapidly in the direction of the gradient of f evaluated at the point 2, 0, 1. All right, so let's go ahead and compute the gradient of f. So this time I'm going to do it and I'm going to put it directly in the vector brackets. So I'm just using a shorthand where I don't write f gradient of f of x, y. So now we're taking the partial of this with respect to x. So we would take the derivative of the inside with respect to x over the inside stays the same. So we get 2x over x squared plus y squared plus z squared, comma, partial with respect to y is going to be 2y over x squared plus y squared plus z squared, and then the partial with respect to z, 2z over x squared plus y squared plus z squared. And now we need to evaluate this at the point 2, 0, 1. And if we do that, we are going to get 4 and 5. So 4 over 5. And then this is 0 over 5 again. And this one is 2 over 5. Oops, I didn't need to do that. All right, so that will be the direction in which f increases most rapidly. Now they also asked for the maximal directional derivative at that point. So the maximal directional derivative at that point is just asking us to take the magnitude of this vector that we have. So the maximal directional derivative at 2, 0, 1 is the length of the gradient of f at 2, 0, 1, which is going to be equal to the square root of 16 over 25 plus 4 over 25, so the square root of 20 over 25. Sorry, I'm out of space. All right, and that will be the answer for number 18. All right, so I'll stop this video here and then we'll continue with example or exercises from sections 13.5 and 13.6 in our next video.